All right, enough here. So we're going to take a look at our kinematics or our motion graphs. And no matter which one you are given, you should be able to use it to help describe how an object is moving. Very first thing you should do with a graph is take a look at what you're actually plotting. So on the x-axis, notice that we have time, and that will be the same for all of our kinematics graphs because we're going to take a look at how things change as time goes on. On our y-axis, notice that in this case we have position, so we can read where our object is located at different times. So if you are asked for your position, literally we can just read the value from the graph. If you're asked something about the initial conditions, like the initial position at a time of zero where this object is located, then the vertical intercept can help you as well. What if you were asked for something that's not directly on the graph? Like I'm asking how fast this object is moving, or what is its acceleration? So, if it's not directly given on the graph, one way you can help yourself try to find the answer is looking on the equation sheet and find an equation that relates both of those axes together. So, an equation that has change in position and time in it. From those equations, if you notice that your variables are being divided out, in the equation, then chances are that the slope will mean something for you. If in the equation those quantities are being multiplied, then chances are the area will mean something for you. And if you're not quite sure, then take a look at the units, whether you divide out the units or multiply out the units. Do they seem familiar to other units for quantities that we have discussed so far? So let's take a look at this. If we take a look at the slope for our position versus time graph, when you do your slope, it is the change in y values, so in our case, change in position, over the change in x values, which would be time. Now, we define the change in position over time as the average velocity. If you didn't remember that definition, take a look at the units of the slope. So you did your y values in meters divided by your x values in seconds, meters per second. Those were the same units as our velocity. Therefore, if you're asked for how fast something's going and in what direction, you're looking for the velocity, then you can find the slope of this graph. What if you don't have a straight line, so I can't just calculate the slope? Well, I can draw tangent lines to the curve at each of those positions. And those tangent lines, if I calculate their slope, I can get my instantaneous velocity or velocity at that exact instant. Also, I could take a look at how those slopes are changing to see what's going on with my speed. So, if the slopes are getting steeper and steeper, then I'm going to increase my speed. I'm getting faster. If my slopes are getting shallower and shallower, so more level, more gentle, then that means that I am slowing down. I am decreasing my speed. Not only can I read velocity from my position versus time graph, but I can also read acceleration. Now, we said that acceleration was a change in velocity. So if you see that this graph opens up and it has this curve, I know my velocity is changing because the slopes are changing. And how is it changing? By positive values. So as soon as you see the graph is concave up or opening up like a smiley faces are positive, then you have a positive acceleration. Reminder though that positive acceleration does not always mean speeding up. Here are the two different things that your acceleration being positive could mean for your motion. On the other hand, if your graph concaves down or opens downward, it's frowning, then you will have a negative acceleration. Again, that doesn't mean that I'm slowing down necessarily, but I will have an acceleration that has a negative sign. All right, now let's do our graphs by looking at a velocity versus time graph. So notice now on the y-axis, we're plotting how fast and in what direction I am traveling. So if I was asked to figure out how fast I'm going at a certain time, I can just look at the value on the graph. If I want to know how fast I started off going, I can look at the y-intercept. Now, another thing with velocity versus time graphs is sometimes I'll just be asking about how the speed changes, and we don't care about direction. So remember, speed is the absolute value of the velocity. So if you take a look at the absolute value of those velocity numbers, or you take a look at how they are coming towards or going away from a velocity of 0, which would be not moving, then you can tell how the speed changes. In these pink sections, when you are moving, when the velocity is getting farther away from the origin, from the velocity of 0, your object would be speeding up. When you have a section of your velocity versus time graph that is getting closer and closer to the x-axis, so towards the origin, towards a velocity of 0, that means you are slowing down. And any place that you have no change in velocity, a constant velocity, so it's not getting farther or closer to the x-axis, it's showing a velocity that does not change for that time period. Let's keep going with velocity. So just like before, let's take a look at the slope and see if it means anything. When I take a look at the change in y values, change in velocity over change in time, oh, that is our definition of acceleration, to change your velocity over a time period. If I take a look at the units for that slope, if I did meters per second, my y values divided by seconds, I'd have meters per second, which can also be written as meters per second squared. And those are also the units for acceleration. So, kind of the same aspect. If you're looking for acceleration on a velocity first time graph and you can't read it directly from the graph, then chances are slope or area, and in this case, it's the slope that means something. Speaking of the area, let's take a look at this. So when we say area, we are meaning the area between where the graph is and the x-axis. So it's kind of like shading in everything under the graph until you get to that x-axis. Lucky for you, in AP Physics 1, all of our areas can be broken down in either rectangles or triangles. So if you can use these two equations, which are also on the equation sheet, or a combination of them, then you can calculate our areas. Okay, so when you do an area, it's some kind of base times height, maybe 1/2 or just a 1. So let's take a look at our base and our height values. So our base is our measure of our x values, which was time, and times our y values, velocity. So if I did velocity times time, well, that is our definition of displacement. And if you weren't sure about that, let's take a look at the units. You took your velocity in meters per second times the time in seconds. Those seconds will cancel out, and you'll be left with an area that would be measured in meters. And those are the units for our displacement. So if you're asked how far you travel and you're only given a velocity versus time graph, then find the area under that curve, and that will tell us how far we have traveled. All right, last but not least, let's take a look at our acceleration graphs. Now, most of ours are going to be horizontal lines because we're dealing with constant accelerations, but you might be asked some conceptual questions about how the acceleration changes. Again, take a look at what's being plotted on the y-axis. We're plotting how fast our velocity changes every second that passes. Some notes with the acceleration. If you have a positive acceleration, remember that doesn't mean speeding up. It tells you the direction that your velocity is changing. So if you have a positive velocity, then you're speeding up. If you have a negative velocity, then you're slowing down, the opposites. Same thing. So remember, opposites mean slowing down. So positive velocity, negative acceleration. Notice your negative acceleration is literally plotted in the negative area. And if you have no acceleration, that means that you are not going to change your velocity. So it doesn't mean you're not moving, it means you're not changing your motion. So this could be an object at rest or an object keeping a constant velocity. All right, so let's take a look at the area because this one is a nice little rectangle that we could take a look at. And notice that this graph is, if I shaded in the area between the graph and the x-axis, I'd have this uh, graph that the square, sorry, this rectangle that is in the negative area. So if I have a negative area, then I do have a negative value for this as well. When you do area, it's some kind of base times height. So for us, our change in acceleration over time. And that's actually a rewritten definition of the change in velocity and our acceleration equation. If you're not sure, take a look at the units. Meters per second squared times seconds. Those seconds will cancel out and you'll be left with one of them in the denominator, so meters per second. Those are the units for velocity. So if I'm asked how much my velocity has changed, and I'm given an acceleration graph, I can look at the area under that between the curve and the x-axis to answer that question. So, just to summarize, we have our three different motion graphs, and either the slope or area can help us determine something that is not directly readable on our graph.